All right, so an essential part of the Artemis program are the human landing systems, or HLS, which will deliver the human crews from spacecraft in the lunar orbit to the surface of the moon. Our senior design project aimed to contend with a major issue that faces the HLS spacecraft, which is plume surface interaction, or PSI for short. The HLS uses rocket engines for its ascent and descent stages, and the exhaust from those engines interacts negatively with the lunar regolith. The lunar regolith is the layer of rocky material that covers the surface of the moon. The regolith grains range in size from the boulder size to the submicron scale. We refer to those smaller particles as the lunar dust, and the lunar dust is hard, sharp, and reactive and can cause a lot of negative effects for the spacecraft. Two of the major effects that we see are cratering on the surface, which you can see on the bottom of this figure, and ejected dynamics, which are represented by the red specks in the simulation. So the ejected dynamics can cause a whole host of negative effects, including creating low visibility for crews during maneuvers, impairing the performance of sensors, damaging structural integrity, and reducing the functionality of mechanisms on the lander. You can see this sort of thing in the sandblasting of metal surfaces and that kicked up dust getting into mechanisms and clogging up moving parts like gears or sliding rails. The cratering can also cause a significant issue because it can create an uneven landing surface. For example, the Apollo 15 mission almost failed because one of the legs of the lander landed in a small crater, incidentally also due to low visibility during landing because of the lunar dust. And that caused a tilt of almost 11 degrees, which was nearly a mission failure because the criteria for that was a 12-degree tilt. So when we consider all those negative effects of the lunar dust, that it can damage critical components on the lander or directly lead to a failure, the business case is straightforward for the CraterGator's lunar dust mitigation device. It's difficult to estimate the exact cost of a catastrophic failure of the lander due to the regolith, but the contract for the Blue Origin HLS was worth $3.4 billion. The predicted cost of the proposed CraterGator's dust mitigation system is $135,000, which, as we can see here, is a nearly negligible cost of that contract for a rather significant payoff in terms of risk mitigation for the mission. Now Erin is going to talk about our design concepts.
Thank you, Kayana. All right, so when CraterGators went about brainstorming solutions for our dust mitigation device, we had to come up with the critical requirements for this Artemis 5 mission for the national team. When going about thinking about these requirements, our number one concern was avoiding as much added weight and cost to this mission as possible. The more weight, i.e. more mass on this big HLS system, the more expensive it is going to be. We do not want to create any more added cost to the national team as possible. We also wanted to avoid non-renewable resources, avoid adding any motion or robotics that could get damaged from the regolith. Avoiding this added motion and robotics will make the device very simple, which will mitigate any sort of, well, it will minimize as much as possible any damages that we might experience. If it's a simple device, then it will be a simple fix. There's less components that are at risk of being damaged by lunar regolith impact during ascent, descent, and landing. Additionally, these requirements that we as a team evaluated was we wanted our device to be flexible to any changing lander designs. As you can see here, we included a few different lander mock-ups, and as you can see here, the design has changed iteratively until during the design process, and we do expect that there may be other engineering designs as national team evaluates their lander design up until the launch of Artemis 5 in a couple of years. And additionally, we also wanted to avoid adding any extra maintenance on the systems. If there are any failures of the dust mitigation device that CraterGator proposes, then the astronauts on the moon will be in charge of taking care of any of those maintenance solutions that they would have to come up with. So with us having a simple design, we want to mitigate any sort of action required for the astronauts when we're on the moon. Okay. Now, Our proposed dust mitigation device by Crater Gators consists of a deflection attachment and carbon nanotube CNT fabric. As you can see here, our dust mitigation device is located on the aft of the lander. And here you can see our deflection skirt, our undercarriage dome, and our CNT fabric, which will be attached to the lander legs. The deflection attachment, like I mentioned, consists of a deflection skirt and undercarriage dome. This undercarriage dome will be located at the very bottom of the lander. And later on in this presentation, you will be seeing the details of how we go about adjusting for the exhaust nozzles that will also be located on the bottom of the lander. Additionally, the deflection skirt protrudes outward right here, and this motion right here is meant to allow for regolith flow to move past our lander and thus mitigate any sort of lunar regolith impact on the base of the HLS. This carbon nanotube fabric will be secured to the lander legs via polyamide tape at the ends, which will allow for the fabric to extend along the legs when landing. The legs will retract during landing.
So going a little bit more in depth with our deflection skirt. So the objective of our deflection skirt is to deflect the regolith from hitting the lander body and also any critical components like sensors that may be on the bottom to assist with landing. In terms of geometry, here's a cutout. It's one quadrant of our deflection skirt. So we have 4 quadrants going all the way around the lander. It's made up of these 3 pieces. We have a thin exterior skin that is connected to our interior supports via welding, and then the interior supports are then welded to the lander itself. So we have one quadrant, and then there's a lander leg on each end of the quadrant. And so then to protect any sort of regolith intrusion based off of these quadrant separations, we have shields on the outside of these interior supports to prevent any regolith from infiltrating the system. Additionally, these are made out of a titanium, tin, aluminum alloy. And so then for sensor recession, we wanted to make sure that our sensors that may be on the bottom to assist with landing are safe from regolith flow. So the way we went about protecting them is based off of the orientation of our skirt on the lander itself. So we see that we have a little bit of a cavity here for our sensors to fit. So what we're expecting is the regolith will flow from the surface of the moon outwards and hit this corner of the lander itself. And so what we're expecting is based off of flow over a ledge, that it will then flow past the ledge up until it hits the next ledge, which in this case would be this outer bottom edge of our deflection skirt. So that is therefore leaving a cavity here for our sensors to recess inside that stagnation point and prevent any sort of regolith interaction with those sensors. In terms of dimensions, our skirt deflection skirt extends 1 meter out from the lander body, and then 1.6 meters in vertical height. And then we see that the bottom surface here is angled 15 degrees from the horizontal, which is helping us with the flow, preventing it from hitting in the cavity for our sensors. Additionally, we have MLI all around the exterior skirt, and it's adhered to the exterior skirt to prevent any sort of tearing of the MLI. Okay, and then I mentioned before that the branches of the interior support are welded to that exterior skin, and then the interior supports are then welded to the HLS itself. And then, as I mentioned as well, the MLI is attached to the exterior skirt with adhesive bonds and covers that entire exterior skin. Here are some material properties of the tin, aluminum, titanium alloy that we chose for our deflection skirt. So we have a high yield strength and a high melting point for any sort of thermal interactions that we will face on the moon. And then fracture toughness in the case of impact from larger regolith particles.
Hello, I'll be discussing one of our static loading cases that we did to ensure that our device wouldn't fail during operation. I'll be discussing the outer skirt as it curves around. In order to simplify the problem so we could perform these calculations, we stretched out the curved shape into a straight beam. We calculated the length of this beam using the angle that it is traveling around and the radius of the section. And then for the loading, it was a distributed load across the length of the beam with simple supports on either end. And then bending was assumed to be the maximum, would cause maximum stress, and the plane of maximum bending would be in the center of the beam. The load was calculated using the acceleration, the maximum acceleration that we predicted our device would see, which would be during launch from Earth. We used the maximum acceleration from the SLS launch vehicle, and while the Blue Moon lander will not be flying on the SLS, the New Glenn vehicle does not yet have data published about its potential max acceleration. Additionally, due to the open cross section that the beam has, we had to take into account the products of inertia as well as the moments of inertia, and multiple points. We calculated the stress at multiple points along on the outer edge to ensure that we found the point with the maximum stress. The point that we had the maximum stress was the far left corner of the beam, and had a stress of 5.35 megapascals. This provided a factor of safety of 154, which is a very large factor of safety, much higher than the industry standard of 1.5 to 2. But we deemed this acceptable as we were more concerned with the potential failure during fatigue or crack growth analysis, as well as the thermal cases.
So the purpose of the undercarriage dome is to deflect the underside of the lander from the regolith that moves upward upon descent. A titanium alloy was chosen because of its high melting point. This was deemed important because the lunar regolith is heated up by the engine plume as it descends, so it needs to be able to withstand those high temperatures. The undercarriage dome is divided into 40-degree sections, with 3 radial sections in each, represented by the yellow, orange, and red. There are also 3 holes in the undercarriage dome, which is where the engine nozzles are located. The sections are connected to each other through electron beam welding. And then the undercarriage dome is attached to the bottom of the lander using internal supports. The undercarriage dome is riveted to the internal supports, and the supports are welded to the bottom of the lander.
A static loading case was performed for the undercarriage dome, just as we performed it for the deflection skirt. So in this case, we simplified the skin of the undercarriage dome for analysis purposes by removing the hole cutouts for the engine bells, as well as flattening the skin. From there, we determined the distributed load Q as a function of the density of the titanium alloy, the thickness of the skin, and the acceleration, the maximum acceleration that the undercarriage dome would experience, which again, just as we did for the deflection skirt, we determined that the maximum acceleration that the undercarriage dome would experience would be the G's felt during SLS launch. From there, we were able to determine the equivalent von Mises stress using the tangential stress, the radial stress, and the weld factor, which we estimated to be 2. From there, we calculated the safety factor as a relationship between this von Mises stress and the yield strength of the titanium alloy. And we determined a safety factor of 3.4, which, although is higher than the industry standard of 1.5 to 2, again, we were mostly concerned with how the design withstood cyclic loading as well as thermal loading, so we deemed this acceptable.
Like Rita said, the most important structural analysis that we took the greatest stock in when we were performing our analyses was a fatigue loading case. Fatigue in this case and cyclic loading was defined not as repeated ascent or descent of the lander, but rather as impact coming from the regolith itself repeatedly during descent. For this case, we needed to establish a load case, which given the wide range of sizes of regolith that the moon has, we wanted to go for something that would create a significant enough load to cause an effect without being so large that it wouldn't actually be kicked up during the surface plume interaction. And so for that, research was done on the sizes of boulders that you might experience on the moon. It's known that around 90% of the regolith on the moon is going to be on that micron level size. And so when selecting a load case, we went for the smallest size that is still deemed as a boulder on the moon and took that to be the load case that we might expect to impact repeatedly. Larger size boulders, we wouldn't expect to see a large amount of kicking up and impacting the skin. Properties of lunar dust regolith were then applied in order to calculate a mass, and then velocity and acceleration that we might expect when impacting the structures was taken from either experimental data on lunar regolith dynamics or information about the Apollo experiments themselves. And this led to a calculated maximum stress in the load case of 532 megapascals. The surface itself was estimated to just simply be a flat plate experiencing cyclic loading. And since the thicknesses of the deflection skirt and the undercarriage dome are consistent and made of the same material, this analysis was deemed as acceptable for both of those structures. All right, so to go through the analysis itself, the amplitude and mean stress were calculated based on that maximum stress on the previous slide and a minimum stress just assuming 0 with no impact. The fully corrected endurance limit and a fatigue strength factor were taken into account as well for our material itself and our geometry. And then an equivalent fatigue strength was calculated using that amplitude as well as ultimate strength of the material and was calculated following the Goodman relationship. The cycles to failure was then calculated using this calculated equivalent of fatigue strength as well as the other parameters discussed. This resulted in a life of 129 cycles. Again, given the variability of the dust on the moon, we were aiming for a cycles to failure somewhere around this range in the low hundreds range for very massive boulders that you wouldn't expect the PSI to even kick up. You would get cycles incredibly low, but for the very small dust, you could get cycles just incredibly high. So this went for something on sort of the average case that we might expect to see from larger size boulders that might impact the structure. And 129 cycles was deemed acceptable in this case, again, based on the statistics related to the size of the regolith that we would actually expect to impact the lander. In addition to this, again, since this was the load case we were most concerned about, we also performed a crack growth analysis. The crack growth analysis was performed around the rivet holes that were going to be drilled into the skin, and that was taken as a potential place where we might see crack growth based off of repeated impact. In this case, the moment at those points was calculated, and then taking that initial crack length, assuming the rivet sizes where we might see a crack form, we were then able to calculate we were then able to calculate constants for calculating, based on the material properties, the constants C and N, for calculating a life during crack growth as well. So able to calculate a range of fracture toughnesses as well as the rate of crack growth, and then bringing all of that together along with the material properties in order to determine that even with a crack at our rivet holes, we could still see a life of 25 cycles. And this was also the range that we were looking for something like this, again, assuming the sizes of the regolith that we would expect to impact our lander.
Another potential failure case for our lander was, of course, a thermal analysis case. In order to do this, we also had to make some limiting assumptions to develop this load case. And so we decided to model the regolith flow as a convective flow. Typically, that's not modeled in a space atmosphere due to the lack of medium. However, due to the multitudes of regolith that our deflection skirt could experience, we decided to model it as a convective flow with the regolith itself being the medium. We also had to determine how what the temperature of the regolith would experience when hitting our deflection skirt. We did decide that the thermal impingement from the engine plume is what would heat up the regolith during flow, and then thus that could get kicked back up and transfer that heat back up to our undercarriage dome. In order to do the convective heat transfer load case, we needed to find the convective heat transfer coefficient for the system. We found Reynolds number, Nusselt number, and Prandtl number via a variety of properties of the lunar regolith, as well as some characteristic lengths of our lander. The Reynolds number proved to us that we were experiencing some turbulent flow, and the Nusselt number and Prandtl number were used via the Reynolds analogy in order to find that H of X, that convective heat transfer coefficient. That, again, is a system property that will help us solve that convective flow problem. And then we wanted to find the heat flux associated with that heat transfer coefficient over the mesh of our deflection skirt via CFD. The results, we found that the undercarriage dome was the limiting case. We did model both the undercarriage dome and the deflection skirt, and the undercarriage dome was found to be limiting. The top, you see a temperature map. The bottom, we see a heat flux map. The temperature map, we see a pretty much constant temperature over the top of our image here. That will be the surface experiencing the regolith flow and experiencing the change in temperature. We found that max temperature to be 73.2 degrees Celsius, which is within the range of the titanium that we chose. Furthermore, we see the heat flux magnitude is at its maximum in this corner. That is expected due to the highest delta T that will be experienced. And that maximum magnitude was around 29,000 watts per meter squared. From that, we decided that it was just a point of something that we needed to reference to and make sure that there was no failure or deformation of material at that maximum heat flux location. And as this is supposed to experience some reflight, that would be a point that our team would want to analyze to ensure it maintained its structural properties.
The other major system on our design is the carbon nanotube, or CNT fabric. This fabric is used to cover the sensitive hydraulic shafts that are on the lunar legs as they extend and retract during ascent and descent. This fabric works because it has a network of carbon nanotube electrodes through it. This network consists of two parallel rows, which have extending columns of carbon nanotubes out of it that do not connect. These parallel columns have 1 millimeter spacing, and when an alternating current is sent through it, it will generate an electric field around the fabric, which will push the charged dust away from the fabric. This design is derived from a spacesuit dust mitigation system, which conducted experiments on a sample of fabric and found that it was 80 to 96% effective on the dust samples they used. The fabric itself consists of an outer layer of ortho fabric, which is 0.5 millimeter thick. This is where the electrodes are actually stitched into. This ortho fabric is a tear-resistant fabric made up of a mix of Kevlar and some other materials. Below that layer is a 0.6 millimeter thick layer of a thermal micrometeoroid garment. This is a mix of 5 alternating layers of aluminum mylar and non-woven Dacron, and then a bottom 0.2 millimeter thick layer of neoprene-coated nylon. This construction allows for it to be fairly resistant against impacts from lunar dust, which will also help during descent and ascent. We conducted an electrical analysis on this to look at the power draw of the fabric. Due to the layout of the fabric, the power draw will come from the internal resistance of the carbon nanotubes themselves. And this was modeled as many resistors in parallel due to the majority of the carbon nanotubes being in these parallel columns. Because of that, we were able to scale up the power draw of the test sample from the experiment. And using our total area of just over 22,000 centimeters squared, we found that at maximum power draw, it will use just under 1 watt. And this maximum power draw occurs during when there is a lot of dust being removed from the fabric, whereas the idle current, which is when the fabric is just sitting idle on the legs, it will use just under 1 milliwatt. Because of this low power draw, we determined that it was adequate to wire this directly to the main battery of the lander itself and did not need an external power source.
As the CNT fabric was one of the more complex systems on our design, we wanted to make sure that there was no thermal analysis, or we wanted to do a thermal analysis to ensure that there was no damage caused to the electronics of that CNT fabric. We decided to model that via radiation in order to identify the heat dissipation ability of the fabric to make sure that any of the power that was being drawn by one section of that fabric, in a worst case scenario, if we assume that all transforms to heat, we ran that radiative calculation and found that the thermal equilibrium was reached at 55 degrees Kelvin. That is under any expected electronic failure of that CNT fabric. We just wanted to make sure that we weren't going to experience, any of that failure. So again, our limiting case is not concerned with the heat generation of the CNT fabric.
So in conclusion, the combination of the deflection skirt, undercarriage dome, and the CNT fabric will allow this design to mitigate the risk of lunar dust of all different sizes. Because these are passive solutions, this reduces the power requirements and minimizes the number of potential failure points. Based on the cost estimations, it also is very cost effective. So because of these factors, this design is a highly effective solution for preventing the negative effects of plume surface interaction. Thank you for attending our presentation.
Great job.
You guys can clap for yourself.
Tom, do you have any question? Ask first.
Oh.
Let's try. Yeah, you can check the chat message. That's why you could have had a high grade for structural analysis.
Yeah, guys.
Who is your audience? Thank you.
Oh, we do have.
I can say it.
Yes, our mass we calculated to be just under 7 kilograms for the entire system. That includes like a bit of extra mass for any weld material.
So before any of you answer the question, you need to read the question first, because when I upload the video on YouTube, there's no chat message shown.
Okay.
Okay.
Question from the audience. The most critical requirement here seems to be, what are you trying to prevent? Can you quantify a target dust mitigation? With our device, we are trying to prevent any sort of failures that would result from lunar regolith during ascent, descent, and landing from getting up inside the human landing system, which will result in failures from sensors being able to analyze how close to the lunar surface we are during those stages of the mission. And so to quantify a target dust mitigation amount, we really don't have the national team's goal for their Artemis 5 mission for this, but for us as a team, that quantified amount is to mitigate as much dust as we can in order for the sensors that are around the aft of the lander to still be able to read like the LiDAR sensors to be able to analyze how close to the surface we are. If there's too much dust, then the sensors will malfunction and we won't be able to get an accurate read as to how close we are to landing. Does that clarify?
Oh, if you want to add like
Yeah, can I add
size.
a little bit to your response?
Oh yeah,
Okay.
I can add a little bit about like size. So I guess the size of dust that we want to mitigate would be from like the small like micron level size with the CNT fabric on the legs, to the like small boulders that could possibly still interact with the plume and impact the lander. So I think that was 2.5 centimeters in diameter was the size of the small boulders.
I was on the fatigue side, yeah. It's not 15. Yeah, like a target amount of regular
yeah.
to like deflect or keep impacting anything. Yeah.
I think that to build on Aaron's response, it's also difficult to quantify because we're also trying to combat the regolith on the submicron scale. And given the information that we have on their specific sensors, the arrangement of their sensor array, and what those sorts of sensors can tolerate in terms of both impact, but also particulate counts in the fluid around it, like parts per million of the regolith. It's difficult to quantify a requirement given that we don't know how their sensors perform.
I can speak about the gaps surrounding the nozzle. I'll hand it off to someone else to talk about the electric field. And also, could you scroll so I could just reread the question real quick?
Yeah.
Sorry. So the question from the audience was he's not actually sure how to quantify our dust mitigation target. The question was, you've got gaps around the nozzle that stuff can get in. Are those okay? You've got an electric field diverting stuff. Is it strong enough? I'm going to speak to the nozzle gaps. So when there have been experiments done where they basically hot fire an engine into some type of lunar regolith situation, and typically the flow that we experience, if we're able to go to the intro slide, and kind of give a little bit more of a visual.
Number 2.
Yeah, number 2, sorry. Yeah, so if we can see here, this is a lot of what we're experiencing. So we see a lot of downward impingement from the thrusters, and a majority of the ejected dynamics are happening outwards of that direct down thruster. So we were not expecting any regolith to be, kind of shot directly back up into the undercarriage of our design. Thus, we weren't expecting any, little particulates to like kind of seek into those gaps right there, which is why a majority of our design was expected to protect this side of the lander. And obviously, as this gets closer to the lunar surface, the cratering goes further down, thus we could experience some more ejecta dynamics closer to the center, but we are not expecting any true lunar dust to be anywhere near those gaps that we have in the undercarriage dome.
And then regarding the electric field, that is specifically for sensitive components like the like hydraulic shafts that abrasive dust might scratch up or get into seals. And is very localized to where the fabric is, and we don't have fabric on the undercarriage dome or skirt itself, as those are not as sensitive as stuff like the hydraulic shafts.
I can also talk a little bit more about like how the like circuitry analysis of this works. Like if you go to this slide. So this is creating an electric field here. We have these two particles that are interacting with these are assumed to be particles of dust that are interacting with the the particles of dust that are interacting with the fabric. And the particles of dust are each creating like two parallel sides, and the fabric itself is acting as a dielectric, which is what's creating this network of capacitors. And then the particles themselves are repelling each other, like they're becoming charged because of this capacitor network, and then they're repelling each other. So the fabric is providing the electric field, and then the particles themselves are interacting with each other so as to like push off of the fabric.
Could you read his comment about?
I would remind you of it time longer. I don't like sand. It's coarse and rough and irritating, and it gets everywhere.
So yeah, I guess also just to go back to quantification, we don't have currently a means to quantify like mass of dust or volume of dust that we're repelling.
Yes. Oh.
So the purpose of that animation is just showing kind of how the dust would be deflected. That is based on the image we have on one of the first couple slides, where we see all those particulates, essentially like, that's what I based that animation off of. It's not necessarily quantified, but that was like the motion that we would expect when landing. Like that's how the particles would move. Yeah.
Specifically for joining the panels of the skirt, we chose welding, specifically electron beam welding, for a couple of reasons. First of all, electron beam welding allows the most retention of strength for butt welds. Other options would have been TIG welding, because that also allows quite strong joints. Another reason electron beam welding was attractive was because it's pretty commonplace in the space industry, And so a lot of aerospace companies would already have access to large EB chambers. And then the third reason that we were attracted to the electron beam process was because it's mechanized. And while for TIG welding, there are some automated processes like your orbital welding or similar. We like that it allowed for a high level of precision when joining those panels together. The reason that we chose to weld the panels together as opposed to having it be one uniform piece is for manufacturability reasons. We were concerned about precision over that large of a part, if it was a single piece. And then also because I imagine it would require some sort of large die to create the curvature that we wanted, and the cost of that sort of fixturing and setup was estimated to be greater than joining panels through welds.
Part of the reason like that we went with welding, because we were looking at rivets, which we did actually use for another fastening component for the supports to the exterior skin, but we were concerned about treating, you know, the lander as a pressure vessel. We were concerned of having the rivets protrude through the lander exterior itself, which is why we went with welding. We found that to be less intrusive to the actual structural integrity of the lander. But yeah. So we don't actually, the question is how much of the vehicle is an actual pressure vessel? So that was something where we were more so erring on the side of caution, where we don't actually have that data from the lander itself. So we could be very low below the crew cabin, and that could mitigate that effect, and we could use fasteners. I think because we were unsure of the layout of the lander itself, we were treating this as our worst case scenario, that the entire lander would be treated as a pressure vessel and could experience some stress concentrations at the rivet impact point.
Nice.
So I guess, yeah, this might be a little confusing. Oh, so yes, for the question is, for the beam analysis of the skirt, are you analyzing the bottom piece of the skirt here, or is this a structural member that's attached to the skirt pieces? This is analyzing the pieces of the skirt, not the support, not the internal supports. Yeah.
It's the support it's the structure, it's the geometry of the skirt, right?
Yeah, this is
Model
the,
as a beam.
yeah, this is the, yes.
Yeah.
This is the geometry of the skirt model as a beam, not including the, like the internal supports that we have on the edges. Just to read the feedback. That's maybe a little to do a beam analysis here. It's a little wide, more like a plate. Not a terrible assumption. The assumption that it's straight rather than curved is a little more dicey. Which, yes, I agree. It's because the curve goes over like almost 90 degrees. Yeah, I'm not sure.
For sake of margin. Like. I think, yeah, we mentioned that times that like typically like that too. As opposed to designed specifically, or means they realize what we before as opposed to like designed it for. I can talk on that. I can address the factor of safety. So it says factor of safety is 154. I'd prefer not to see a realized factor. Mentioned a few times, it would be 1.5 to 2. Prefer to hear you say this is a factor of safety we're working to, and then a presented margin of safety to show that you met it. Yeah, this is something that definitely this was one of the more complex, I think, parts of our structural analysis that we had to work through, is the simply supported beam analysis was definitely allowing for a much like weaker material than the fatigue analysis was allowing for. So in the pure static loading case, the design is essentially over designed. But if you design it specifically for the static load case, and then you put it into the fatigue analysis, you'll see it fail instantly as soon as it gets hit by something. And so that's just to answer the question about the large factor of safety. As far as the presentation of it, which I think is mentioned here as well, that's probably something that we could have stated a little bit better, the reasoning or group the results a little bit better to show that. But that's more so behind the large factors of safety on the static loading, is that it's designed to not just break at the first cycle of impact from the boulders.
Yeah. I want to say that there's some mistake for the evaluation. So can you change the fatigue analysis? I think there's some mistake there. So for the fatigue analysis, the only way you can use the equation is when the fatigue cycle is between 10 to the third to 10 to 6. That is the stable propagation phase, and that is the equation to model that phase. Below 1,000 cycles, we cannot really use this equation. So when you get it like life cycle 129, it's not really in the region that we can use this fatigue equation. Do you guys remember the log scale like SN diagram, and it's like initial propagation and stable phase and rapid propagation, and this straight line in between, that is second phase, and that is the phase that we can use this equation. That's how the equation we derived. So if you want to use this equation, the range is 10 to the third to 10 to 6. If you're outside this range, this equation really cannot use in like 129 cycles.
Okay.
Yeah. So probably this part we need to redo it.
That's fair. Or medium design, but I guess specific, we're just aiming for like a range.
That is correct. Yeah, we were comparing the temperature of the plate via our CFD analysis to the melting point of the titanium.
You guys.
Oh, is it because the properties change as it got hot anyways?
Yeah, it's still not bends, so.
Yeah.
I definitely think that's valid. I will say we were concerned not with the like plume itself interacting with the titanium skirt. We were more so concerned with the plume interacting with the regolith and then the regolith flow transferring that heat back up to the titanium. But yes, agreed that before melting point, there is some deformation and structural properties that will change due to the impact of that temperature. We are also very far from the melting point. I believe it was around 76 degrees Kelvin that we were experiencing via our CFD analysis, and the melting point was around 1600. I'm sorry, not Kelvin, degrees Celsius. 73 degrees Celsius was our max temp over the flat plate, and then the titanium melting point was around 1600 degrees Celsius. Yeah, the values for the yield strength are above that as well, but that was not taken into consideration when we did our thermal analysis. That was our hope as well. Sorry.
Yes, we could still consider it, but we should keep that engaged.
Don't want to have one of those like Mars Explorer moments, whatever that one craft was. They used a contractor. They used English units instead of
Right.
In order to, or the question is, how did we get the stress for the impact?
Man, it's a net system.
It's also the TA speaking, that's not one of us.
In order to get the maximum stress, I'm the one who did this and calculated this load case. I did some research into the sizes of regolith that are expected on the moon and what is qualified as a boulder, the smallest diameter boulder that we could experience, which is where the initial, like the boulder diameter came from. The density is then pulled from the properties of just lunar regolith, specifically focusing on the rocks themselves, not necessarily just the dust. Mass, again, was pulled using properties of the regolith, and the velocity and acceleration I gathered from research on how the regolith reacts when the landers are landing, especially from the Apollo missions. I was able to find that data and employ this. I was able to find velocity. I wasn't able to find acceleration data, so that is an assumption that if we have this velocity, then just using that with the acceleration, just assuming a time that's involved. And then the maximum stress was calculated then using that force that I got from the boulder size and acceleration, just like F equals ma, and then applying that to the plate itself. And it was a flat plate using the dimensions of the deflection skirt, a deflection skirt quadrant. Yeah, there's definitely a lot of there's definitely assumptions in this load case, which definitely something to look into a little bit more, modeling the impact, the way that the dust is kicked up was something that definitely like that we tried to do this just as best we could with the information that we had, but in order to come to a stress that we thought might fall along like the average size, but the numbers themselves propagating into the stress, there definitely could be some improvement made there in terms, because there are a lot of assumptions in work. Mm. Yeah. Lower sensitivity in this. Yeah, we'll definitely take a closer look at our fatigue case based on the feedback that we've gotten. Forced stress.
Thanks, like you try to point load at the center of the page.
Oh, yes. Yeah, to go from the force itself, we're applying a force at a point in the center thing. Yes. Oh, using a hand count to come up with stress, the answer is yes. That's what we did.
Question, you mentioned that the CNT capacitive system was 80% effective in testing. Yes. 80 to 96%. More details on that. They used the JSC1A dust sample, which is based on volcanic ash, which has very similar properties to lunar regolith or the lunar dust. The way they did that test is they had the sample at I think about a 40-degree angle and sprinkled. They had different trials, but some they sprinkled the dust on and saw how much stuck, and some they just had it coated and activated the system and saw how much was removed. The question was, what did that test look like, and how does that extrapolate to how you're doing it? We're doing it in a fairly similar way as their system was mainly static, as well as ours is mostly static as well, and is very similar conditions, except I guess ours will be in a vacuum, whereas they just did it in the atmosphere. If you go to one of the slides with the lander picture itself. On these lander legs here.
No, which one do you like?
Oh, that one. Yeah. You can see there's sections of the lander legs covered in MLI, and then there's sections that are like shiny shafts. We assumed that based on the geometry of the lander and how it has to fit in the payload fairing, that those legs have to extend or retract during the launch of the payload itself, and then have to extend during descent and ascent from the lunar surface. And from our research, we found that those hydraulic shafts are fairly sensitive to, potentially abrasive dust, and damaging those seals and sticking to those shafts as they retract. So we're trying to protect those shafts from the dust, specifically the like micron scale dust. The question is, are those legs going to actuate after this thing lands? Like, can it extend the legs when it's reasonably far from the moon? Would it ever retract? That we don't know entirely. But depending on how it maneuvers, especially with as it potentially docks with other spacecraft, there may be a reason to retract it, but we don't know for certain, as that information is not available.
Yeah, we were taking one section of one of the legs, so there's 4 legs on there. We were just doing the analysis of one of the sleeves of the CNT fabric. The assumption was that we were going to be landing on one of the poles of the moon, which is typically not in sunlight. So we were assuming it was not experiencing any thermal radiation from the sun. Again, we are not entirely privy to that information, but during our analysis, we did assume that we were landing in shade.
I think the question is like, could we land in sun if we had to?
Oh, sure. Yeah. We didn't do the analysis on it. I don't perceive it would be a problem if we were landing in any type of thermal radiation from the sun, but obviously we would have to do some more experiments and do some more analysis on that via modeling that thermal radiation. Yeah, again, we're mostly concerned about electronic failures, so that's what we'd be focusing on for the CNT fabric thermal analysis. Definitely fair. I do believe that the CNT fabric is not expected to draw much more than a milliwatt of power. So I think the assumption was that there wouldn't be a culmination of both power generation and thermal radiation from any type of solar impact, but that is a good point.
Keep in mind too that as far as the Blue Origin plans go, it sounds like they want to have at least a 2-week time extended stay, with the assumption that they're going to be in, as I recall, from solar exposed times where they could use their solar arrays to generate power, and then they also needed fuel cells for times during shady times. So there's more than likely going to be a chance that there will be enough time and rotation of the moon in which they will be exposed to some amount of sunlight.
Yeah.
I understand it, so.
Completely fair. Yeah, we would definitely need to do an analysis of thermal radiation impinging on the CNT fabric.
Part of the reason we didn't worry. Part of the reason we didn't worry about the radiation from the sun as well is because the construction fabric is based directly off of spacesuit fabric, which is currently used both in the heat and cold of space. So we weren't worried about the sun damaging it at all.
Could the material be brittle?
Again, the question is, if 55 Kelvin isn't too hot, is it too cold? This is all, like I said, based off the spacesuit fabric, which is currently used, in space and has been, tried and tested. So it is not expected to have any problems at those temperatures. The actual electronics that are in the fabric itself are just the carbon nanotubes. The actual, battery system is internal to the lander itself. So there aren't really like electrical components other than the carbon nanotubes themselves that could get damaged by the cold. The resistance of the CNT fabric to debris kicked up by landing is a small concern, but again, based on the construction, it's made out of very tear resistant materials, and it's also not too sensitive to damage as well as the actual driving electrical components are within the lander itself. So it is not expected, although it may see some damage from potentially small boulders. It is expected to be fairly resistant.
Yes, currently our budget is just materials. We attempted to take into consideration how long it may take to manufacture and assemble these, like these large assemblies, but that was difficult, and we weren't able to determine the value in time for this presentation. The majority of the material cost is for I believe it's for the titanium like alloy sheet metal. And the CNT fabric costs that like 30K, so I guess the 100,000 in the sheet metal and support structures. Thank you.
Thank you, Tom.
Thank you.
Thank you.
We really appreciate this. So I think people are waiting outside. So I just want to put all the comments. Really great presentation and the detailed amount of work. I really appreciate that.
We got until 2:30. I have any questions, a few questions asked, but after you're done.
Yeah, so I think and the presentation part is like really, I mean, everybody did a really great job, and also the Q&A part, I'm glad to see that I'm glad to see that everybody get involved, because in our previous group there like one or two super strong students, they answer 100% of questions. It's like the rest is silent. I'm glad to see that like everybody in this group are very strong and involved in the Q&A session. And okay, thank you.
Thank you.
First of all, I want to apologize for being a little bit late, but you guys did a great job in your presentation for what I saw. But I've just got 3 questions that are kind of, well, I would track that too, because they're itching at my brain. In terms of like how the skirt is and its geometry and relative to the legs themselves, how do you expect the legs to contract exactly? Because
Yeah, I guess we didn't show it very well.
Yeah.